Okay, so continuing with our SAT videos, again, this is the calculator questions. I recommend that you pause when a new problem comes out, give it a shot, and then I will show a couple of ways to solve it. So give this one a shot. Okay, so John runs at different speeds as part of his training program. The graph shows his target heart rate at different times during his workout. On which interval is the target heart rate strictly increasing, then strictly decreasing? So in here, strictly increasing means going up. Strictly decreasing means going down. So let's look and see what we have here. So we can see here it is strictly increasing, here it is strictly decreasing, then strictly increasing. We have some constant values here, and I need to figure out when this happens. So between 0 and 30 minutes, I see that it is increasing, but then constant. So this is not my correct answer. Between 40 and 60 minutes, I see that it starts going up, so strictly increasing, then goes down, and doesn't level off, doesn't come back up till after this window. So this is my correct answer. Between 50 and 65 minutes, let's see, 50 to 65 minutes, I have this other case where it starts decreasing, then increasing. And finally, 70 to 90 minutes, it is constant, has a jump, then is increasing, then is constant again. So it doesn't have this strict increase, strict decrease. And strictly increasing means that I will not allow it to be constant. Okay, give this problem a shot. All right, so in solving this, if y equals kx where k is a constant, and y equals 24 when x equals 6, what is the value of y when x equals 5? So this is a situation called direct variation, and I have a relatively simple way I can do this. I can basically plug in my known information. So my known information is that y is 24 when x is 6, so I can take this equation and put that information in and know that then, okay, y, which is 24, will equal k times whatever x is 6. Solving this equation, I'll divide 6 from both sides and get that k will equal 4. And then I can use that information to rewrite this equation with my known k value, so y equals 4x. And when x is 5, I will get y is 4 times 5, which will be 20. Now, other things that you could do. So one possibility here is that if it's a direct variation, if I know that y will equal something times x, then to go from 6 to 24, I knew that I had to multiply by 4, and I can use that rule to see that, okay, then when I start at 5, I better end up at whatever 5 times 4 is. That's 20. And basically, this is linear, so I can use any of my line tools that I have, knowing that the y-intercept is 0. Okay, give this a shot. All right, so a little bit of geometry. In the figure above, lines L and M are parallel, and lines S and T are parallel. If the measure of angle 1 is 35 degrees, what is the measure of angle 2? So there are a bunch of ways to get around here. One of the most mathematical ways would be this. So I could first realize that this angle here, so this is 35 degrees. I'll make this an x for a brief second. So these two angles are what's called a linear pair. And so that means that I know that x plus 35 degrees is 180 degrees. And by subtracting 35 degrees from both sides, I can see that x will equal 145 degrees. And then, since S and T are parallel, this angle here will be congruent to this angle here because they are corresponding angles. And for a very similar argument, since L and M are parallel, this angle here will be congruent to this angle here because they are corresponding angles. So this will also be 145 degrees. Not the only method. I could use vertical angles. I could use alternate exterior angles and same side interior angles. There's many ways to get across there. But that's one way to realize that the measured angle too has to be 145 degrees. Another option, so whenever I have this diagram where these two pairs of lines are parallel, I basically have a situation where all of my angles will either be x or 180 degrees minus x. There will be just two situations. So in here, 35 degrees, 145 degrees, 35 degrees, 145 degrees. And that, it's really nice. It's sort of a shortcut. It's not great because it requires these are parallel and those are parallel. But the problems you see will most likely have these parallel and those parallel, so you can use it. And so even though I have 4, 8, 12, 16 different angles here, I could just list them off. Every acute looking angle will be the same as whatever one is, which is 35 degrees. Every obtuse looking angle will be the same as whatever this adjacent angle to 1 is, which is 145 degrees. And so I can use that to just list all these: 145 degrees, 35 degrees, 145 degrees, 35 degrees. I can go around, I can put all these angles down here. So that's worth noting for problems like this. Give this a shot. All right. If 16 plus 4x is 10 more than 14, what is the value of 8x? So if I just use this, I can set up an equation. So 16 plus 4x is, so 16 plus 4x, 10 more than 14. So is 14 with 10 more. And I can set that equation up and I can solve it. So I could combine these like terms and I would get 16 plus 4x equals 24. I could subtract 16 from both sides and get 4x equals 8. I'm going to put that minus 16 there for us. I could divide by 4 and get that x equals 2. And then I can come back and look and see that I want to know what 8x is. So notice they have a 2 here. This is the wrong answer. Don't pick it. I want to know what 8x is. I know x is 2, so I do 8 times 2 and get 16. Now, you could do a couple of other things. I could just plug in values and put in 2 and see that 16 plus 4 times 2 gives me 24, so it works for the equation, and then try to figure this out. Another better thing that I could notice, not necessary but better, is I could take a little bit of a detour here. If I keep in mind that I'm not actually trying to find what x is, I'm trying to find what 8x is, I could actually take this information and just say, okay, if 4x is 8, then 2 times 4x, because I want 8x, should be 2 times 8. And I can get straight to 8x equals 16 without getting the unique value for x. All right, give this problem a shot. All right, so a little bit of statistics here. Which of the following graphs best shows a strong negative association between D and T? So for these scatter plots, we have two descriptors for the correlation. We have this word strong, we have this word negative. So I guess let me change the color on that so I can talk about them separately. Okay, so first off, this word here, we would be looking at something like strong, moderate, weak. I could also see things like perfect correlation or approximately no correlation. And basically, what this says is how close, you don't spell close with an S at the beginning, close to an increasing or decreasing line we are. That's important, increasing or decreasing. This word negative, we have two choices here. We could either talk about positive correlation or negative correlation, and these are directly tied to slopes. Positively correlated graphs will tend to go like this with a positive slope. Negatively correlated graphs will go like this with a negative slope. And if you ever get confused about that, notice that for positive slope, positive correlation, as I go right, I go up. We read from left to right, and I will look at lines and correlation from left to right. A negative correlation, as I go right, I go down. So again, from reading from left to right, talking about going that way. So now, looking at this, I want strong negative, which means close to a line, but decreasing. So this is maybe decreasing, but it's not very close to a line. So that's not my answer. This one definitely looks like a positive trend. As I go farther right, the points tend to get higher. So this is not my answer. This one, now here's a case that I want to stress. This looks almost horizontal, and the points are relatively close to that horizontal line. Notice how I said close to an increasing or decreasing line? This would be approximately no correlation. I'm not going to get too deep into it in this video, it's not the right place for that, but just to try to say correlation tries to describe the change in t by changes in d. In this case, you can see as d increases or d decreases, t doesn't seem to change. It always seems to be around the same, being stuck in this type of interval, no matter how large or how small d is, with slight changes. So that's why this is, even though it looks like it's close to a line, this is approximately no correlation. Finally, by process of elimination, we get to D. D, we definitely have a decreasing regression line, a negative trend. As D gets bigger, T gets smaller. And it looks relatively close to a line, so the only case where I have the negative trend and close to the line is D. All right, hope that helped out. We'll have another one up for tomorrow.